Welcome back. Hope you're doing well. A new location, a new haircut for a new unit that we're starting today. Hope you are doing well. We have been discussing linear algebra and looking at operators on abstract vector spaces over the past few months. Now, what we want to transition into here is to continue to abstractify another area of mathematics, and that's going to be the area of analysis, of calculus, if you will, to be more specific. So we're going to be looking at the calculus sequence now, going through the kind of hitting the highlights of calculus 1 through 3, but attempting to come at it from more of a generic context. And the way that we can do that is we'll still be talking about the real numbers here, but we're going to start opening the door for what if we weren't working on the real numbers? What if we were working on things like functional vector spaces and things like this, things with similar sorts of properties to the real numbers. Now, again, we're just going to be focusing on the real numbers for now, but what we're going to do is start talking about the topology of the real line in order to get us started here. The reason that we're talking about this is that sometimes this is not in your typical advanced calculus or beginning or intermediate real analysis course, but sometimes what we're going to be looking at is a notion of closeness inside of our space. And that's what we want to do here. We're going to treat the real line as a topological space. Essentially, we're going to talk about its topology a little bit, talk about what it means for points to be close or far from each other, in terms of what are known as open and closed sets. This is the notion of topology. We can do topology in any sort of topological space, and this can be a wide variety of spaces. And so being able to have this framework at hand is useful and important for knowing how to deal with other more abstract types of spaces. So we'll be doing a little bit of this here in the real line to get us started. This will also help us continue to make our proofs more rigorous as we go through and see these things in the calculus sequence. Hopefully we've done this a little bit at some point in an undergraduate course, but this will be in some sense a good refresher while also taking us a step forward. Now, I will mention that in this unit, we are going to be skipping over things like sequences. You may remember that beginning of advanced calculus usually go over things like convergence of a sequence. You're going over things like Cauchy sequences. You're going over the monotone convergence theorem. And then usually you end up with talking about series a little bit as well. We are only going to be mentioning these topics as they become useful for us in talking about things like functions, since that's usually where calculus 1 begins. So it might be a good idea if you are interested to be looking at and touching on some of the other resources that we have at hand if it's been a while since you've seen these sorts of things. For example, Thomson-Bruckner, one of our texts, you might want to go ahead and check out the first few chapters in that textbook and trying to read through those to remind yourself, okay, what does it mean for a sequence to converge again? What was that definition? Because as we continue through these next few sections, I see that what we're doing is topology of the real line, limits of functions, and then immediately followed by continuity. Usually this is something that only happens in the second half of an advanced calculus course. So the first half is going to be assumed. So make sure that you're checking in on those, looking through those proofs, becoming a bit more familiar with that. It is going to be useful and helpful to be looking at those things there. But let's go ahead and get a little bit of an introduction to topology of the real line. Let's go ahead and be drawing some pictures here. You're going to see that I have a lot of blank slides so that I can draw a lot of pictures as we begin discussing topology here in this context. Let's start with an epsilon neighborhood. You may be familiar with the notion of epsilon from sequences. For all epsilon, there exists a capital N, a cutoff point, if you will, for your sequence, such that for all elements of your sequence past that cutoff point, the absolute value of your sequence element minus your limit, right, your place where it's going to, that is continually waning down. That window is going to be eventually less than epsilon. Right, that's our notion of the limit of a sequence. And one way that we could classify that is that instead we could say, let's say we have an epsilon neighborhood of a point X that contains all points of distance less than epsilon from X. So another way that we could write the definition of a sequence now is we could say for all epsilon greater than 0, that is for a sequence S of n converging to L, is that we could say for all epsilon greater than 0, there exists a cutoff point n such that for any n greater than n, it is true that S of n is in an epsilon neighborhood of L. So that is, Sn and L are within epsilon of each other. So that means that Sn minus L is either in between negative epsilon and epsilon. Hence, S sub n is going to be inside of L minus epsilon to L plus epsilon. So the difference between these, an absolute value, is less than epsilon. So that's one way to kind of see how this thing could be in play. And now this notion of epsilon neighborhood has more to do than just working with the sequence of a limit. Epsilon neighborhoods are useful because you can in some sense say what points are close to it by determining how many epsilon neighborhoods it's in. In some sense, what is the smallest possible epsilon that is a neighborhood of this point x, such that this other points that I'm looking at is still inside of that epsilon neighborhood. Past a certain point, it's not in there, but this other point might be, so this point is closer inside of that sense. So that's a lot of what topology is trying to do, is use these notions of things like epsilon neighborhoods to discuss things that are close to specific points. Like S sub n gets closer and closer to L, which means it's in more and more epsilon neighborhoods. Eventually, it is going to be in any epsilon neighborhood if you go far enough. Now, let's keep classifying these types of points when it comes to looking at these in terms of sets. For now, we're going to be specifying, let E be a subset of R. Again, here, when we say subset, it could mean that it is equal to, so I want to make sure that we fix that notation. Sometimes you see this notation instead for is a subset or is potentially equal to. And sometimes instead you'll just see here, this means is a proper subset of. We are not going to use that notation. We are going to say that E is a subset of R to mean either E is a subset and not equal to R, or E is equal to R. So it is possible for E to just be a subset of R, including being equal to R itself, whenever we make this sort of notation. That's the notation we're going to be using throughout this course. So now, with this set in mind, let's talk a little bit about what all points and sets and how these things can be related here. Let's talk about the beginnings of point set topology. Now, the point X, if we have a set E and we want to talk about how X is related in situation to E, then there's a couple of different ways to think about how this picture works. Let's say that our set E is something like this. Well, the point X could be right here. That could be a place where the point E is going to be. It is in the inside of the set E. Another place that the point could be is that the point could be outside of E. That could be in the exterior side of it. One other place is that the point could be right on the boundary of the set, right? There could be some part of it that looks like it's kind of, you can see, because I have some thickness to this point, some of it looks like it's inside, some of it looks like it's outside. Maybe we could say it's on the boundary. So interior, boundary, and exterior points all have to do with this sort of picture. Namely, we have to generalize the fact that, well, whenever I don't have a picture, I don't have thickness to our point. So in particular, how am I supposed to be able to deal with this? How do I say that something is a boundary point? How do I say that something is an interior or an exterior point? What we end up doing is we start talking about these points in terms of their epsilon neighborhoods. Namely, for an interior point, you can see there exists an epsilon neighborhood that is completely inside of the set E. And that's exactly how we clarify that the point X is an interior point. If for some epsilon, notice the difference here, it is not for all epsilon greater than 0. This is for some epsilon greater than 0. The entire epsilon neighborhood, x minus epsilon to x plus epsilon, is contained in E. We want the whole thing to be contained in there. And an exterior point is kind of done the same way. When in the interior point, we say that there exists an epsilon neighborhood that is completely inside of our set E. Now, if we're looking at an exterior point, we would want there to be an epsilon neighborhood that is completely outside of the set E. That means that it is clearly on the outside part. So this is going to be what we say when you have a point X that is an exterior point of the set E. Now, you might think that the boundary point here, that this green point, is actually also an exterior point. Because if you look at this set, it seems like my notation seems to imply that the endpoints of our set are kind of like if you look at an open interval, for example, like this would be outside of the set E. So why is it not an exterior point? Well, because we have a specific name for points that are on the boundary of a set. Notice, for example, that this point is not an exterior point by our definition. It's not an exterior point. And the reason is that whenever I take an open interval around that, I cannot ever find an open interval that is constantly outside of the set. That is completely outside of it. All epsilon neighborhoods have some parts that are inside and some parts that are outside. So because of this, we say that this is going to be a boundary point instead. So the point X is a boundary point. Notice that all of these definitions are all going to be like they're going to be mutually disjoint from each other. You cannot have something that is both an interior and an exterior point, right? Because if you have some epsilon such that is completely contained in E, you can't also have an epsilon neighborhood such that the point is disjoint from E. That would be a contradiction from how those two sets work. The boundary point says that for any epsilon, you have some points that are in E and some points that are not in E. So that cannot be an interior point because it's got points that aren't in E for any epsilon. And it can't be an exterior point because it's got points that are in E for any epsilon. So all of these three things are mutually disjoint from each other. These are all three different definitions. So if something's an interior point, it can't be the other 2 points. So you can see here with this remark, every interior point must belong to E, every exterior point must not belong to E, and boundary points can be or not be inside of E. They could be one or the other. For example, if this had been a closed bracket here at the end of E, the green point would have been inside of E, but would have still been a boundary point, thanks to our epsilon neighborhood definition. Now, we didn't have to do this just on the real line. We could have been doing this in R squared as well. Right, so you can start taking a look at sets in terms of how they look in a multidimensional context. So for example, if I have a set like this, then I can start doing the same thing in terms of inside, outside, and boundary points, respectively. But notice that epsilon neighborhoods here are going to be slightly different. No longer are they just going to be on a line in some sense. Our notion of an epsilon neighborhood is going to mean that you're kind of looking so that any distance from the point X, say, to any other point is going to be less than epsilon. So this might be an example of what an epsilon neighborhood looks like in terms of R2. It looks kind of like a little circle, right? Notice that it's an open circle. I've made a dotted line there because I am not including the boundary of that circle. Same thing over here in the purple part, you can see that there is a particular epsilon neighborhood that keeps you completely outside of the set E. And then finally, for the boundary point here, any circle that I draw around this blue point is going to be part in and part out of the set E. So you can see here, I've drawn examples of interior, exterior, and boundary points as well in terms of R2. And we could have done this in terms of R3 or R4 and any of these other things, because all of these spaces have a defined notion of distance. Well, what else do you know that has a well-defined notion of distance? That's right. Any sort of normed vector space has a notion of distance. Our Hilbert spaces have notions of distance, which and we haven't been calling them Hilbert spaces because those are complete, my apologies. But we've been talking about them as inner product spaces. For inner product spaces, you can define norms, and for norms, you can define distances. So you could do a similar thing and write a similar definition if instead of trying to do things in terms of open intervals and little open balls, you instead said the distance from a point to any other point is less than epsilon. So let's go ahead and keep looking at these examples in terms of just the real line for now, but we'll keep trying to generalize these to more general contexts, especially to R2 as we move along. Let's let E be the open interval from A to B. Now the interior points of these, remember that every point that's inside the set must be an interior point. Well, let's make sure that that's true, actually. Every point that is an interior point must be inside the set. The opposite is not necessarily true. So that's a good point to kind of clear out. The interior points are these points A to B. So any interior point must be inside of the set because we know that for any point X inside of, any point X inside of AB, we know that X is not A. We know X is not B. And because of this, there's going to be some distance, some wiggle room that the point X has before it reaches the boundary points at A or B respectively. In fact, those are the only boundary points of this set. Those are the ones that if you took open intervals around the points A or B, you would get just that there is going to be some points in and some points outside of our set. Now, everything else is an exterior point. Everything else, all of the points outside of the closed interval going from A to B, those are going to be our exterior points. So that helps classify all of these points. You might notice that there's a little bit of a pattern here, right? These three sets are all mutually disjoint from each other, and also they make up the entire real line. Let's go ahead and see if that continues as we look at the closed interval going from A to B. Notice that the interior points for this one are exactly the same. It is still the open interval going from A to B. So interior points are points of the set, but it's not necessarily true that all points of the set are interior points. Not all points of the set are interior points. For example, A and B being points in this closed interval are not interior points. They are still boundary points. The idea is that our picture from before, even though we include two more points in our set, it hasn't really changed in terms of its epsilon neighborhoods. You still have for any epsilon neighborhood of A or B respectively, some points are within the set, some points are outside the set. Similarly, the exterior points are all of those outside of the closed interval because now you have a little bit of wiggle room to write one of those epsilon neighborhoods. And then finally, the set going from 0 to 1. This is a half open interval, closed at 0 and open at 1. Union with the half open interval going from 2 to 3, closed at 2 and open at 3, has its own interior points. The interior points being the open intervals 0 to 1 and 2 to 3. You might notice that's a little pattern here as well, that the interior points are always forming open intervals whenever they're being made. That's an interesting point that maybe we'll get to talk about in a little bit. The exterior points also form open intervals, and these stretch far beyond where the points are. Notice they are not including 1 and 3, even though 1 and 3 are outside of the set E, they are not exterior points. Instead, they are boundary points, as are 0 and 2. So this is another good example for looking at these in terms of this. Another example that we could be looking at in terms of R2 is we could be looking at sets like this, xy, such that x squared plus y squared is less than or equal to 1. And we can ask the question, what are the points that are boundary points, interior points, and exterior points for each of those sets, right? So if we're drawing this, we know x squared plus y squared equals 1 is going to be what? That's right, it's going to be a circle of radius 1. You can draw it all the way around. And you can ask the question, what points are going to be interior points of this set? Well, this whole set, if I'm drawing it right here, it's going to be this entire thing. So I'm drawing in and putting in everything in there. And if I want to draw an interior point, well, I'm probably going to choose points like that are inside of here. Now, probably not points in here. Like that's not going to be an interior point. And the reason is that that point on the little boundary there, well, I'm already saying that it's boundary. On the boundary of this set, it makes more sense that it be a boundary point. That is, any epsilon neighborhood that I draw is going to have some points inside and some points outside of the circle. So here is an interior point. Here is an exterior point. And then here is do a different color here. Here is a boundary point for each of these. So if we wanted to classify what each of these were, then we would say, let's say this is the set E. Then we would say the interior of E, and I will abbreviate that by writing INT-E. So this is going to be what I mean when I'm talking about the interior of this set. The way that I would classify is what? I would say it's all the points x and y such that what? It has to do something with the circle. So we should know that x squared plus y squared and 1 are going to be part of this. But what's the connection between them? Notice that we do not want x squared plus y squared to equal 1 because those would be points on the boundary. So instead, we're just going to say it's going to be less than 1. Anything that's equal to 1, instead, those are going to be the boundary points. That's going to be all of these xy. Those are going to be boundary points. And I will say b dy of E, b dy for boundary. And then I will say ext of E to be all of these points such that you're on the outside. X squared plus y squared is greater than 1 because for these points like those out here, you can draw little epsilon neighborhoods that are completely outside of our set E. So here is an R2 example. That's a good one. Now, there's more examples in terms of the real line to be looking at, such as the real line itself. What if we make our set the real line? Well, what do you think? What are going to be interior, exterior, and boundary points? Well, interior points, well, everything is inside the real line. And indeed, there's no real notion of thinking about how you would make a boundary of a real line if there's no real separation between outside and inside, because it's all the real line. It's all inside. So every point is interior. There are no boundary or exterior points for this set. What about the empty set? The empty set similarly has no separations. So there shouldn't really be any boundary between it. But this time, there's no point inside of the empty set. All of the points are outside of it. So it makes sense that every point is exterior in set. And indeed, there are no interior or boundary points. Now, another good and interesting part is to look at the rational numbers. Recall that we know a good bit about the rational numbers. Namely, the rational numbers are dense. The rational numbers are dense inside of R. And what does that mean? What does it mean for rational numbers to be dense? That means for all open intervals inside of R, that the rational numbers intersect with that open interval is non-empty. That means every open interval, if you look at it, you can find a rational number inside of there. It is the intersection of that open interval with the rational numbers is going to be non-empty. In fact, you could go through and show there's infinitely many rational numbers inside of that open interval, if you would like. So what does this mean for us? Well, we know that the rational numbers are going to have non-empty intersection with any open interval. Well, what does that tell us about exterior points? Remember, exterior points means if you take an epsilon neighborhood around the points, there exists one of those epsilon neighborhoods that does not intersect the set Q at all. But that means none of those can exist. None of those can exist because any open interval, remember epsilon neighborhoods, they're open intervals. If you intersect them with the rational numbers, well, it's not empty. You're always going to find a rational number in there. So that means that there can be no exterior points. But similarly, we could do the same thing with the irrational numbers. The irrational numbers are also dense. So that's why we could say that there's no interior points either. Another way to think about it is that between, like, you can't find an interval full of just rational numbers, right? You're always going to be able to find an irrational number in there. What does that mean? That means every open interval that I pick, right? I can center it anywhere. I can pick any epsilon neighborhood. There's always going to be a rational point. There's always going to be an irrational point. That's exactly the definition of every point of R being a boundary point for Q. So we've kind of broken apart what it means for every point to be interior with the real line, every point to be exterior with the empty set, and every point to be a boundary point with the rational number. So these are some good examples to be thinking about. Let's go ahead and see a few more. What about the natural numbers? The natural numbers also seems like it's a little bit tricky to think about an interior of the natural numbers, because if I draw this picture, what does this look like? Well, you have, starting at 0, perhaps, you've got 1, 2, 3, 4, 5, and so on. Each of these points seem rather isolated, you might say. They kind of are very far apart from any of the other points that exist inside of that set. So these are very isolated points in their own right. Now, that means that there cannot be any interior of the set. 1, for example, if I were to take a look at 1, notice that all epsilon neighborhoods contain 1. So 1 is going to be an element of the set, and hence it can't be just completely outside of the set E. However, it also contains any of the points right outside of 1. The ones that are a little bit less than 1 and a little bit more than 1 are all also inside of that epsilon neighborhood. Because of this, it means that every natural number is a boundary point. But it also means that that can't be an interior point. So we know that there's no interior points at all, because we could have done this at any natural number. So there are no interior points. Now, all the other points, then, that means must be exterior points. And how does that make sense? Well, if I take any point outside of here, I can always find an epsilon neighborhood that's small enough such that it doesn't contain any of the other natural numbers. Even if it's 1.00001, you can still make an epsilon that's smaller than that 0.0001. And then at that point, you can say, okay, anything inside that epsilon neighborhood, it doesn't include a natural number because it's far enough away from 2, and it doesn't include 1. So any of those points, then, we could include all of the complement of the natural numbers inside of the real line. That union of open intervals is the set of exterior points. We could also look at sequences as well. Let's remember that a monotonic sequence is a sequence that is either constantly increasing or decreasing. And by that we mean either it's for any n1, say that n1 is less than n2 when n1 and n2 are 2 elements in your index of your sequence. And that's going to imply that S sub n1, the element of the sequence itself, is less than or equal to S sub n2. And if that's were to make case, you'd have an increasing sequence. But you could also have it be the case that whenever you increase your index, you have your S sub n1 is greater than or equal to S sub n2. Some people will call this non-decreasing and non-increasing, respectively. So that might be another thing that you see sometimes in our terminology whenever we go through a reading. But we can generalize all of this by saying that this is a monotonic sequence. Notice that a monotonic sequence that is bounded has a converging limit. And indeed, this seems to be bounded above by 1 and below by 0, since all of these terms are going to be positive. Indeed, this sequence is of the form S of n equals 1 over n. Now, the sequence S of n equals 1 over n, if I'm trying to figure out where that converges, well, there's kind of one place that makes sense, right? It converges toward 0. So that's exactly what we're going to use here. Now, when I take the set of all of those elements of that sequence, what do I get for its boundary, interior, and exterior points? Let's draw it. The picture is going to be, we have 0 here, we have 1 over here. And if I draw the points on this, I'm going to have starting with 1, then I'm going to go 1/2, then I'm going to go 1/3, 1/4, 1/5, 1/6, and so on and so forth. And you see that kind of what's happening is that I'm continuing to make more and more dots as I get closer and closer to 0. But the question is, are any of these points going to be interior points? The answer is no. Even though if I look closer here, it looks like a lot of the points touch each other. That's because whenever I draw a picture of this, there is a kind of a vision problem that we end up having of just drawing the picture and instead of seeing what it actually is. That is, these points have thickness. And the point 1/5 is not going to have any thickness to it. It's just going to be the point 1/5. That means anything in between 1/6 and 1/5 is not inside of this set, for example. All of those are going to have to be exterior points. Well, what about 1/5 itself? Well, any epsilon neighborhood around 1/5 is going to contain a point inside of the set containing 1/6 to 1/5. But it's also going to contain 1/5, so it ends up being a boundary point instead. So that's why every point inside of this is going to be a boundary point. Every point inside of E is a boundary point. Notice that 0 is also a boundary point, because any epsilon neighborhood that I make around 0, even though 0 itself is not inside of this set, and keep that in mind, it's only the elements of the sequence, not the limit itself, that's inside here. But any open interval containing 0 is going to contain at least some 1 over n. It's going to contain at least something. It just has to be small enough to fit inside of here. It could be 1 over a million. But it will eventually sit inside of there. So there's, for any of those epsilon neighborhoods, you can always find a point inside of this set. But you're also going to have 0, and 0 is not in the set. That means that it is a boundary point, not an interior point. Notice that there are no interior points thanks to what we were describing before, which means all the other points here are exterior. So all other points that we have not been describing, the points outside of E and 0, those are all exterior points. So now we can talk about these definitions that we've been using. We have a set of all interior points, which is its own set. We're going to call that the interior of E. A set of all boundary points, that's its own set, is the boundary of E. And sometimes instead of how I called it, like B dy of E, you will see it called like this. That looks kind of like the little bit of a partial derivative symbol, or at least half of it, the upper half of it, to mean the boundary of E. This is the parts on the kind of the rim of that circle that we were drawing before. And then the set of all exterior points is going to be called the exterior of E. Now that we've gone through some examples, these propositions should hopefully kind of fall out. The exterior of the set E is the same as the interior of the complement of E. Okay, what does that mean? Let's draw a picture. The exterior of E, remember our pictures from before, that the interior of a set, remember, is going to be kind of like the open intervals that include the insides of whatever point that you're looking at. So for example, if I were to draw the interior of a closed interval, then I would be looking at this open interval right here. That would be the interior here. Now the exterior means it's all the other stuff, not the interior, not the boundary. It's all of those points that have an epsilon neighborhood completely outside of the set. But remember that way that we drew that picture was that it looks like this. It's all the stuff to the left and all the stuff to the right of this closed interval. Well, what have we just drawn? Notice that this is all of the stuff that is in the complement of this set E. More particularly, even if we hadn't had a closed interval here, if we'd had an open interval, then this complement, this part that we've drawn for this exterior, would be the open intervals. And that's kind of all the biggest open intervals possible that exist outside of this set. That is exactly the interior of this set. It is the interior, all of the things that are outside of that. So the exterior of E is the same as the interior of the complement of E. The boundary of the set coincides with the boundary of the complement. If I had taken a look at the boundary of 0, 1, right, then those boundary points would have been 0 and 1. But if I had taken a look instead at the complement of that, all of the points that are outside of it, notice negative infinity and infinity, those don't count as boundary points. They are not inside of the real line. 0 and 1 are the only boundary points possible. So that is an example of where you can see this proposition coming to be true. And then finally, one of the propositions that we discussed already is that the real line is the disjoint union of the interior, the boundary, and the exterior points. Every point is exactly one of these. It cannot be more than one. It cannot be less than one with relation to any set. Another neat little thing here is that the interior of the set, like we've seen, is contained within the set itself. But if you add in the boundary points, remember, boundary points are either in or they're not in the set, but exterior points we know are certainly not in the set E. So whenever I take a look to see where E actually lies, it's somewhere in between the interior, which is all inside of the set E, and the interior, including the boundary points, essentially excluding the exterior points, which we know are not inside of the set E. So that's a neat little thing. We're going to keep talking here about some of the other types of points that we're going to be seeing as we go through and see these things in topology of the real line. So far, we've been discussing things and really trying to hammer home this notion of interior, boundary, and exterior, because any point can be one of these three things. Now, there are more points out there, though, and more points that are interesting to us, because essentially what we want to do at some point is talk about these different types of points, as I've been characterizing sets themselves, as when is it the case that, like, for example, the interior of the set is equal to the set and things like this, or when is it the case that the boundary is always included inside of the set itself. Those are going to be notations that we're going to want to talk about in a little bit. But for now, let's keep talking about these other types of points. Let's begin with a definition. A point X is called a limit point of the set E if there exists a sequence inside of the set. So that means that each of these X of 1, X of 2, X of 3, all of these are individually inside of the set E. And X of n converges to X as n goes to infinity. So that it means that the sequence of X of n converges to that point. Notice that it is not necessarily true that X is an E. It's possible that X is an E, but it's not necessary. So for example, for the set 0 and 1, you could say 1/2 is a limit point, because I could take a sequence of elements inside of this set that converge to it. I'll tell you the sequence: 1/2, 1/2, 1/2, 1/2, 1/2, and so on. Why does the sequence work for the definition of limit point? Because every point inside of that sequence is already an element of the set. 1/2 is already inside of the open interval going from 0 to 1. And a constant sequence of 1/2 converges to, you guessed it, 1/2. That means that 1/2 is a limit point. So 1/2 is a limit point of the set. A similar notion shows that every point that is already inside of the set is already a limit point of it. But guess what else is a limit point? 0. Why 0? Well, we've talked about how the sequence 1/2, 1/3, 1/4, 1/5, and so on, that this converges to 0. Notice that every single point inside of this sequence is going to be inside of our set, and that it's converging to 0, which is not inside of our set. Because of this, 0 is a limit point, and this also shows that it's not necessary that our point need to be a set inside of the set in order to be a limit point. So the remark shows our 1/2 sequence, for example, the elements of the sequence need not be distinct. So every point inside of it is a limit point, thanks to our definition. One theorem here that helps us characterize limit points is in terms of epsilon neighborhoods. So let's talk about that. A point X is a limit point of a set if and only if, for all epsilon, the epsilon neighborhood going X minus epsilon, X plus epsilon, contains at least one element of E. Does this remind you of anything? Notably, interior points are going to be this way, because any epsilon neighborhood that you choose, there exists an epsilon neighborhood that is completely inside of the set E. So for any epsilon smaller than it, it's still going to be inside of the set E. So you can get the for all epsilon from that. But something else that would be true about this is what? Boundary points. Boundary points would also fit in here. The reason boundary points would fit is that for all epsilon neighborhoods of a boundary point, You're going to be, part of you is going to be in E, part of you is going to be not in E. So those boundary points are also going to be limit points. And that gives us this corollary that the set of all limit points of E is the interior union with the boundary. No exterior point gets to satisfy this because there exists an epsilon neighborhood completely outside of the set E, which is the negation of this statement. All right. Now we can break down the notion of limit points a little bit farther. We've already seen that you can break down limit points to be interior and boundary points. But there's another way to break these things down. Let's talk about it for a little bit. Let's talk about accumulation versus isolated points. What's the difference between these two things? An accumulation point is going to be a point of the set E such that for any epsilon greater than 0, the epsilon neighborhood contains, get this, infinitely many elements of E. Infinitely many elements of the set E. Now, what does the infinitely thing matter? Well, take, for example, the natural numbers. If we look at the natural numbers here, and I'll draw this right up above here. Remember that the natural numbers, you start at 0, and then you have 1, 2, 3, 4, and so on. All of these are going to be points inside of our set E, and we can agree with this. So for any epsilon neighborhood, you're going to have a point inside of your set E. But here's the thing. Once your epsilon is small enough, you only have one point in there. You only have one point of the set E, being the natural numbers, of your epsilon neighborhood inside of that little set. So if E is the natural numbers, and epsilon, for example, is less than 1, then 1 minus epsilon, 1 plus epsilon, the intersection of this with the set E is just going to be the set 1, which means that it has cardinality of 1. It's not an infinite number of points. So this point by itself is not accumulating points that are around it. That's why we say this is not an accumulation point. There's not infinitely many elements inside of any epsilon neighborhood that I choose. Instead, what we do is we call this an isolated point. This is an isolated point of E because there exists an epsilon such that x minus, such that that epsilon neighborhood around that point is just that point. It's just the point x. It turns out that these two things are disjoint from each other, and these two things together, union together, make up all of the possible limit points. So this is good for the natural numbers. What about for the rational numbers? Would the rational numbers be accumulation points or isolated points inside of their set? Well, think about how the rational points are kind of strewn throughout, right? You kind of like the rational points all exist throughout this entire set. Right? It seems as though they kind of do, when I draw a picture of them or do my best to attempt at it, they do all seem to kind of accumulate around each other. They're not the entire set itself, but remember, any open interval around any point is going to have infinitely many elements of the rational numbers. That is in the definition of density. So it turns out that the rational numbers are accumulation points of their own sets, whereas the natural numbers are isolated points of their own sets. Now, notice that there's nothing in here about the points that we're talking about, x. They don't have to be inside of E. They could be outside of E, right? So, for example, we could go back to our example of, let's see. We could go back to our example of 1, 1/2, 1/3, 1/4, our monotonic sequence here. And we can ask the question, is 0 an accumulation point or an isolation point, or an isolated point? And after thinking about it for a little bit, you might start falling into one camp or the other. You might say isolated point because, well, 0 kind of, it does feel like it's all by itself. It's the only limit point of this thing. But I think a lot more evidence lies behind the accumulation point argument. And here's why. For any open interval that I choose around 0, we know that eventually there's going to be some 1 over n that's inside of there. Well, then what's going to be true about 1 over n plus 1? 1 over n plus 1 is going to be less than 1 over n, so it's also going to be inside of that epsilon neighborhood, as is true for any other value that is greater in its denominator, because that's going to be a smaller number. So there's infinitely many points in any epsilon neighborhood that you choose. That gives you that by definition that it is an accumulation point, right? So because there are, if 1 over n is less than epsilon, then if n is greater than n, that implies that 1 over n is also going to be less than epsilon, right? So these are all going to be inside of our little epsilon neighborhoods there. So here is our theorem for accumulation versus isolated point. A theorem for the accumulation point is to say this. Instead of talking about infinitely many points inside of our set E, let's talk about it this way. Let's take a look at the epsilon neighborhood without the point X itself, like without the natural number points. So for example, let's take a look at this epsilon neighborhood, but let's ignore one. How many points of the set E are inside of that epsilon neighborhood? None. The only point there is the isolated point. And that's exactly what our theorem is saying, is that something is an accumulation point if and only if, for any epsilon that you choose, you still have one element of E that's different from X. You still have something that is not the point X inside of that epsilon neighborhood. Because if you don't have that, you're looking at the natural numbers, and that's more of an isolated point rather than an accumulation point. Now, the corollary of this is that the set of all limit points is the disjoint union of the set of its accumulation points and its isolated points. Notice that this is all limit points, not just points of the set itself, but also those on the boundary of the set. Those can be broken up into accumulation or isolated points as well. Let's go through a couple more properties to end us out here. Or rather, I think we just need to, we'll say what we've kind of said a little bit already, just as a quick slide to kind of clarify what we were saying. Every natural number is an isolated point. There are no accumulation points. Every element of E itself, notice that 0 we said was an accumulation point, but note that every element of E is itself isolated in terms of its picture, because all of these points, no matter where they are still some distance apart from any other point. And then the rational numbers, every point is an accumulation point for Q. Notice that's every point, including the irrational numbers, because even epsilon neighborhoods around irrational numbers still contain infinitely many rational points. And that means that there are no isolated points, thanks to our little corollary, or our corollary from before. So now let's close by talking about some properties of what are open and closed sets. Let's wrap everything up in terms of it's talking about limit points, accumulation points, interior points, exterior boundary. Let's talk about how we can classify things as open and closed. An open set is going to be a set such that every point of E is an interior point of E. Notice that the opposite is already true. Every interior point is already a point of E. However, we're saying that a subset is open whenever you can flip that. Every point of E is an interior point. For example, the open interval going from A to B. If I wanted to find the interior of the set, which you already have, we know that the interior of AB is just the set AB itself. So that means that every point of E is an interior point of it. That means that this is an open set. But open intervals are not the only open sets around. You could also have A, B union CD, because if I had taken the interior of this, I would have gotten the same interior. Notice it's no longer an open interval. It's a union of open intervals, and this is an open set. Now, closed sets are going to be not necessarily just not open. This is something that is a good thing to kind of keep in mind when we're making this definition, is that just because something is not open doesn't mean that it's closed. We have to kind of shake our door analogy a little bit here, right? Because when you think of a door, it's either open or it's closed, right? And there's this notion of like cracked a jar. Well, maybe it's kind of open, kind of closed. We don't have that notion here. Open and closed are just two properties that something can have. It is true that open sets and closed sets are different for the most part. There are some sets that are both open and closed, and there are a lot of sets that are neither open nor closed. So that sort of analogy, keep that out of your mental cage for a little bit, because open and closed are just going to be properties that mean they kind of look a little bit like open intervals if they're open, and closed is going to mean, as we're going to see, closed sets are complements of open sets. Now, because now there's going to be plenty of sets that are neither open nor closed, so there's going to be a lot that's in the ether there that it's neither of those two labels. But we do know that open intervals are going to be open sets. Open intervals are going to be open sets. Closed intervals, well, each of these contain their limit points, right? For example, remember that we had the example last time of 0 to 1, and we said that you could take the sequence 1/2, 1/3, 1/4 eventually, and get that this sequence limited to 0. But 0 was not inside of our set if it was an open interval. Now, if it's a closed interval, it does include 0. It includes the points on its boundaries. It includes the points on the very end. So closed intervals are going to be closed sets. You know what else is going to be a closed set? Just the singleton sets, just the set containing a single point. The set containing 0 contains all of its limit points, because what sequences can you get out of the set containing just a single element? Well, only the constant sequence A, which converges to A. So it contains all its limit points because it only has one. It only has the limit point A. So that would be a closed set. So it's not just closed intervals that are closed sets. Now, these 2 points clarify what I was talking about before. If a set E is open, the complement is closed. And if a set E is closed, the complement is open. And you can check this out. You can try this. If I had taken the complement of this set right here, for example, I believe I would have had like a closed interval inside of them, and then two closed intervals going off toward negative infinity and infinity, respectively, on either side. Those are all contain all their limit points. So that would be very good for a closed set condition. Now, there are both closed and open sets. And there's not many of them. In terms of the real line, there's only the empty set and the real line itself. You can check to see that these all contain their interior points for the real line. For example, the real line, everything is an interior point. So of course, every point of R is an interior point. And it contains all its limit points, because any sequence inside of R converges to a point in R. So it's a closed set, an open set. Same thing can be done for the empty set. But it is also true that these are the only sets with these properties. The only set that is both closed and open, or the only sets that are closed and open, are going to be the real line and the empty set. Those are the only two. Now, the intersection of 2 open sets is open. So, for example, if I took 2 open intervals, intersected it, I'd get either nothing or an open interval. Both of those are going to be open. And you can do this in more generic context for any amount of open sets. If we said U1 and U2 are open, then we can say that U1 intersect U2 is also open. Now, the union of any collection of open sets, notice not an intersection, but a union of any collection of open sets is also going to be open. And you can go through and prove this yourself if you would like. In finding the interior of each of these open sets, if you try and union them together, you're kind of unioning the interiors as well. Now, you cannot say that about closed sets. In fact, the flipped part of this is true whenever you talk about closed sets. Notice the intersection of any 2 open sets is also open, and the union of any collection of open sets is also open. Notice that this is something that's more finite in nature, and this is something that could be infinite in nature in terms of the intersection and union indexing sets. The opposite is true for closed sets. The union of 2 closed sets is also closed. Now, that's true. Now, the intersection of any collection, however, for infinite collections of closed sets, is also going to be closed. Let's go ahead and see some counterexamples real quick. Let's show the union of any collection of closed sets is not necessarily closed. And the example that I want to use for this one is something like this. I want to go through and use something like, let's do 1 over n and 1 minus 1 over n. Let's say that this is the set AN. Now, we can only start looking at this set whenever n is equal to 2, for example. Then we have the set going from 1/2 to 1/2. It's just a singleton point, which we know is going to be closed. Any of these other sets, like 1/4 and 1 minus 1/4, if I'm looking at A4, is just the set 1/4 to 3/4. That's a closed interval, and hence it's also going to be closed. However, the union of each of these A sub n is going to be what? Any ideas? Can it contain its limit points? Can it contain 0? If it contains 0, you have to say what set it's in. It's going to have to be in some A sub n. But no set A sub n contains 0. Because notice, it all stops before you get to 0, regardless of what n is. But it will include any other point before that. So notice that this union is just going to be the open interval from 0 to 1. This is open, not closed. The similar thing can be shown for the intersection of any collection of open sets. And we can see that this one is not necessarily open. You might already know that this is true because you could just apply De Morgan's laws to the example that we just done here and realize that this is just kind of like the opposite statement. So De Morgan's laws already shows us this other statement based off of what we've shown right here. But we could also just give another different example. The intersection, as n goes from 1 to infinity, of the open intervals, 0 to 1 over n. In fact, let me do it a little bit differently here. Let's do it like this. Let's do from -1 to 1 over n. This is going to be the set -1 to 0. Notice it includes 0 because 0 is in every single set here. But it cannot contain any points that is above 0. So this is not an open set. -1 to 0, it contains something that is not inside of the interior. 0 is not an interior point of the set. So this is not an open set here. So this is not open. That will do it for us today. We've gotten a little bit of an introduction here into the topology of the real line, especially giving us some good counterexamples to help us through and note all of these different types of points and sets. All right, this is a good thing to kind of keep in mind, and we are going to be using this sort of terminology, especially as we go through and talk about functions and continuity in the future. But that will do it for me today. Thank you so much. Have a wonderful day.